So our next speaker is Arjun Radhakrishna from Microsoft. He will present this very exciting work on FlashFill++. If you're all fans of FlashFill, you'll be excited about this one.
Okay. Can you hear me at the back? Please wave. All right. Excellent. So this talk is about FlashFill++. Right? So before we go into the plus plus part of it, let's talk about FlashFill a little bit. So FlashFill came out of this paper by Sumit Gulwani in POPL' 2011. So this has been 10, 11 years now. And what it does, it's a synthesizer for string transformations. So you give an example, and the synthesizer learns a transformation in the background, a program that transforms the input into the output. And here is how it works in Microsoft Excel, right? So here the leftmost column is the input, and here the first row is an output. And based on this input to this output as an example, it has synthesized a program and has filled out everything else in gray text. And you can press enter and it will fill it in. Now, this feature in Microsoft Excel has millions of users each week. And it's been called the best feature of Excel, like the most amazing feature and everything. But the coolest thing, which I think this is the only POPL paper I know about, it's actually the origin story of a superhero. I see some skeptical faces, but here you see Miss FlashFill. So Miss FlashFill created this ad to advertise her Excel tutorials. So, by the way, just to be clear, we are not affiliated with Miss FlashFill. So that's just someone we don't know, right? So it's been 10 years since the feature came out. And since the past 10 years, our team has been getting a few repeated asks. One of them is show me the code, right? Excel users are not experts, so if they see a transformation, they see the outputs, they're happy. But if you go to any level of expertise that is even one step beyond, like data scientists or a business intelligence analyst or any of these people, they're like, oh, show me the code because I don't trust your transformation, right? And the other thing is, we have all these Microsoft teams who are saying, oh, I want code to be generated in Python or in SQL or in M or PySpark or whatever, right? There are lots of different languages. And to be clear, this is the code generated by FlashFill. Don't look at the code and ask me questions about this because I don't understand it, right? So the problem here is not just about simplifying this code. So let me show you why. So here's an example I have at the top. This was my flight, and I wanted to figure out what state I'm flying to. And here's the Python code that does this, right? So it says, oh, find the first parenthesis, and from that index, find the next parenthesis, and then the following closing parenthesis, and extract between those two positions. So that program, that's how you would do it idiomatically in Python. You could probably use regexes and other things, but this is one good way of doing it. Now, if you go to the Power Query M language, this task is common enough in Power Query that there is a text dot between delimiters, starting delimiter, terminating delimiter, and the instance of the substring you want to extract. So it's like, if you write this code in M, it's not idiomatic. You want to use this function. Similarly, like here's another case where I want to find the last day of a month. And a very good way of doing this in Python is saying, find me the first day of the month, add 1 month, and subtract 1 day. That's the easiest way I could think of writing this function. But an Excel user, like people who are doing reports in Excel, do this task all the time. So Excel has an end of month function, right? So it's not just about translating code that was generated into a different language. Like different languages need different programs to be synthesized. So idiomatic program translation is as hard as synthesis, right? So the second thing people have been asking us for a while is date, time, and numeric transformation. So here is some record from CSV, and there's a date and time here, and I want to bucket it into weekdays and like 3-hour periods. So tasks like these, right? And FlashFill cannot do this. FlashFill doesn't understand dates, doesn't understand times. So here's a very a tweet that was retweeted like several thousand times. So DEC goes to December, NOV goes to November, OCT, October, April, August. So this is like a very common scenario. Like people in our team have got mail, like physical mail with dates like August, right? So somebody's used FlashFill and like has not really looked at the output. So the thing that people want from date, time, and numeric transformations is things like parsing, rounding, bucketing, formatting, these kind of things, right? Rather than arithmetic. It's more common that people want to do this because it's easy to write a plus. It's harder to write a round. And also date, time, and numeric transformations, they have very highly varied standard libraries in different languages. So each language has very different date time functions, for example. And it's among the most requested FlashFill extensions. So to satisfy these two asks, we needed a change of philosophy. So FlashFill has a small but very expressive DSL. So if you really look at it, like the original FlashFill DSL had only 3 string functions. So there are 3 very messy string functions. And the idea was you limit your search space a lot, and you write a synthesizer that's highly optimized for these 3 functions. And translation is hard, right? Because these are these very messy functions that I don't know how to translate idiomatically, right? Now the FlashFill++ approach is you go to a really large DSL, like you have over 25 string functions, over 40 functions, but we use a more scalable synthesis technique. So you add all the weird functions that all these target languages have into the DSL, and you use a more scalable technique, and that gives you a much simpler translation. So let me talk about this more scalable thing, right? So I had this slide. So rather than doing top-down synthesis or bottom-up synthesis, we are doing something called middle-out synthesis. So Wusuk has gone over top-down synthesis and bottom-up synthesis like already. I'll go over this quickly. So let's say I have this example, first name, last name to last name, comma, the first initial, right? So how you do like top-down value propagation is using something called witness function. So you start with the output, and for each function in the DSL, you say, oh, what are the values that can give me, what are the input values that can give me this output? So here I can get this output by concatenating A and the rest of the string, or I can get it by AH and the rest of the string, and so on, right? And you have this big tree and you can keep exploring, and here I say, I can get this by taking the substring of the input from the 5th position. And you explore this tree, and at some point, you'll end up with either all inputs or constants. So what you're doing is, you take the output, you repeatedly apply these inverse semantics functions, or what are traditionally called witness functions, and you get the input, and until you get a subtree that only has input values or constants. And the DSL author actually writes these inverse semantics functions or witness functions. Now, bottom-up value propagation is the opposite, right? You start with the inputs or constants, and you keep applying all possible forward semantics. So like functions in your DSL, until you end up with the output. Again, this is, the DSL author has to write the forward semantics, but this is usually much easier than writing inverse semantics. So let me show you a problem with this, both these approaches. So I have this example here that says the price is $24.58 and 46 units are available. And I want to return 24.00, the number. So like the way to do it is you round, you get the substring that represents 24.58, you parse it as a number, and then you round it down. Like this is the program we want to end up with. So if I start doing inverse semantics, there are an infinite number of numbers that can round to 24, right? So this is an infinite width tree, and I can't really explore it easily. If I start with the input and do forward semantics, I can keep exploring this, I can keep applying this, but there are so many substrings, most of which won't parse as a number, right? Like this is not an infinite width tree, but it's still a really large width tree. So this becomes expensive again. So we have introduced this notion called cut functions. So what cut functions are, if you think about this pipeline going from the input to the output, like starting from top, you get an infinite width tree. Starting from the bottom, you get like a really large tree. But there is somewhere in between where the width is very bounded. So if you look at like what functions what substrings can go through this whole pipeline, there are very few of them. There is 24.58, there is 46, and there are these tiny substrings, right? 2, 4, 4.5, and so on, right? These are significantly smaller. So like this is the idea of a cut function. So a cut function is something like, if a program P contains a substring within a parse and returns a non-null value, then the substring should return a numerical substring, right? This is like a very simple idea. And that is what the cut function for parse and substring is, right? So it's like an invariant for programming by example. So like if something goes through here and comes out there, there is a invariant here that has bounded width, right? So now given these few values here, I can do something very interesting. So I can say, oh, let me take this 24.58 and I break it up into two tasks. So the outer task, which says starting from 24.58, I want to get 24. So here the substring is an input variable. So I say, oh, substring is an input variable that has value this much, produce the output. And then there is the inner task, which is to say, take the whole input string and give me that substring. Here, like the substring is the output terminal. So I split the synthesis task into two smaller subtasks, right? I can do this for 46 as well. And this one will give me a result, and that will be my, that will be the result of my synthesis. So here's a rule. I'll just flash it because I haven't talked about any notation here. So let me flash away. So this idea is called middle-out synthesis. So top-down synthesis is basically saying, oh, what operation produced the output? So what's the top-level operator? Bottom-up synthesis goes the other way. What operations can I apply on the input? So you go the other way. So this middle out synthesis is saying, I'll determine some intermediate value and split into two subtasks. And this intermediate value given by the cut function is written by the DSL author. So like the person who's designing your synthesizer will also write the invariant, right? So just to summarize, so cut functions are these invariants that will help you break up your problem into two smaller parts. So this is very much like what you would do in program analysis. If someone annotates an invariant in between, you can sort of reduce it into two smaller problems, right? So that's exactly what's happening. So the other thing is cut functions you can use them to judiciously introduce incompleteness. So I've been talking about these two numbers, 24.58 and 46 in the previous example. But there are all these other random numbers, right? So a DSL author can decide, oh, if I want if something is flowing into parse number, I would like that function to be maximal. So they can tune this cut function for incompleteness. So there's also another technique, which I'll not go into detail here, but we replaced our ranking functions, which is like, originally they were like weighted automata over trees, with something called precedence guided ranking, which sort of amounts to lexicographic path orderings plus some weighted ranking functions. So this sort of lets you eliminate bad branches very quickly. But also, the FlashFill ranking function was highly tuned over a lot of time. And within just a couple of weeks of development, like these this more complicated looking ranking functions were able to gain parity, right? We didn't need to tune it as much. So let me go to the experimental results. So we compared FlashFill++ with FlashFill and Duet. So there is also comparison to another tool in the paper, but that has a lot of asterisks, so I'll not go into it. But overall, like from a variety of benchmarks sourced from a lot of different places, FlashFill++ was able to solve like 92% of the benchmarks compared to just 65% of the baseline. So it does much, much better. On the other hand, like I noticed that it required slightly more examples than FlashFill. So it required like on an average 0.2 additional examples per task, right? But then we looked at it like the tasks FlashFill++ solves are inherently more ambiguous. So if you look at this date, 1/1/2023, and translate it to Jan 1st, what should be returned on for this one? And the answer depends on if you're American or not, right? And here's another numerical rounding thing where you like round up or round to the nearest, so these kind of things, right? So like the way I would take this is you need almost the same number of examples per task despite solving harder tasks. So the third thing we want to look at is performance. And here, the harder the task gets, like the more, the better FlashFill++ is compared to FlashFill or Duet, like the best of the two. And the final thing, the way I started this talk was with readability, right? So this was a program produced by FlashFill. Now this is the equivalent program produced by FlashFill++. Like this task is doing some, take the first initial, take the last name, do some business with the numbers here. This is way easier to understand. However, we can go one step further. We can say, oh, like take the FlashFill++ program and use codecs to rename all the variables. And then what we get is like, oh, first initial is the first letter of name, the number prefix is the first 4 letters, and this is a way more understandable thing, right? So we took all of this Oh, by the way, just intermediate thing, like FlashFill++ programs are usually like around 70% shorter than FlashFill programs. But so we took these three things. So there's FlashFill, FlashFill++, and FlashFill++ with renaming, and did a user study, right? And 98% of the people agreed that FlashFill++ was way more readable than FlashFill. I don't know what the other 2% were thinking. I think they're wrong. So, and about 86% said that variable renaming is helpful, right? So there are people who don't need variable names. So again, that's interesting. So there's also like the thing saying, oh, is A similar to the code I would write, which FlashFill only 13% say yes, 80% say yes for FlashFill++, and with the renaming, 91% say yes. And these are actually very interesting quotes from the participants in the survey. The first one, they say just confusing, simple and direct, tells a better story. I think that summarizes it. So let me flash this conclusion slide, but this is the last slide, so it's available now out in Excel Online, Power Apps, Power Automate, and we are getting really good reviews, so go out and try it. Someone says they saved 16 hours of work just 4 days after release. I don't know who's writing Excel formulae for 4 days, 4 hours a day, but there's that user. All right, any questions?
Thank you, Arjun. Let's thank Arjun. Questions?
So you mentioned that one of the motivations for this work was the second ask for users within Microsoft to have the expressions in Python or R or M or whatever. And so you introduced a lot more, I guess, primitives in your DSL. So what happens when a target language doesn't have all those primitives? How do you make sure the translation still remains idiomatic?
Oh, you can disable those functions and run the synthesizer, right? So depending on the target language, you can choose the subset of the DSL that's important to you.
Great talk. How many more hours are the DSL experts spending on FlashFill++ with these cut functions?
So this is a very interesting thing. So the one of the authors, wait, how do I do this? So Clint Simon, who did most of the work on the DSL authoring, is an engineer. He's not a researcher, has no experience in this field before. And he did it over a couple of weeks, but sort of slowly adding this, right? So it's not too much more too much more effort. And these cut functions, you don't need to write it for all pairs of non-terminals, right? It's one of those, if it's available, we can use it. If not, like, let it go. Yes, but maybe I can explain it to you offline.
Hey, Arjun.
Hey.
Great work. So my understanding of all of these like fun cut elimination theorems are because actually choosing that center value is kind of very difficult. And so I'm a little interested, if you're doing this middle out synthesis, how are you able to identify this center value in a way that doesn't become hopelessly heuristic or lose completeness?
So again, I think the answer is related to these canonical cut functions. I think what we are looking for is a part of the DSL which has non-effectively invertible functions at the top and non-effectively enumerable functions at the bottom. And whatever is in the middle is the thing that needs a cut function.
All right. I know that everyone has more questions, but we need to move on to the next talk. Thanks again, Arjun.